Warm greetings to you all. Today I, Srijana, and Soumya Agrawal of class 10th A is going to present our science exhibition project on the topic Story of a Black Hole and its Utilization. So let's begin. In this project we are going to cover following topics, and the topics are: what a black hole, how does a black hole looks like, can we see black holes, formation of black holes, type of black hole, death of black hole, extraction of energy through black holes, black hole versus white hole. In this project, we will expand our knowledge about black holes and know more about the cosmos. Ever wondered that an entity such as black hole, which has immense amount of energy packed into it, can be utilized and harnessed? This project will help you understand more about such topics such as black holes, formation of black holes, white holes, and so much more. So let's begin our journey to the cosmos. Another most fascinating and strange object in space is black holes. Don't let the name fool you. A black hole is anything but empty space. Rather, it is a great amount of matter packed into a very small area. The result is a gravitational field so strong that nothing, not even light, can escape. And anything that ventures too close, be it a star, planet, or spacecraft, will be stressed and compressed like a putty in a theoretical process aptly known as spaghettification. So to sum it up, black holes are points in space that are so dense that they create deep gravity sinks. Ever wondered how does a black hole look like? Black holes have three layers: the outer and inner event horizon and the singularity. The event horizon of a black hole is the boundary around the mouth of its black hole past which light cannot escape. Once particle crosses the event horizon, it cannot leave. Gravity is constant across the event horizon. The inner region of a black hole where the object mass lies is known as its singularity, the single point in space-time where the mass of black hole is concentrated. Scientists can't actually see black holes the way they can see stars and other objects in space. Instead, astronomers must rely on detecting the radiations black holes emit as dust and gas are drawn into the dense creature. But supermassive black holes lying in the center of a galaxy may become shrouded by the thick dust and gas around them, which can block telltale emissions. Let's see how black holes are formed. The most common way of formation of black hole is by stellar death. As stars reach the end of their lives after using last of its fuel, most will inflate, lose mass, and then cool to form white dwarfs. But the largest of these fiery bodies, those at least 10 to 20 times as the massive as our own sun, are destined to become either super-dense neutron stars or so-called stellar mass black holes in supernova explosion. However, as the star collapses, a strange thing occurs. As the surface of the star near the event horizon, time on the star slows relative to the time kept by the observers far away. When the surface reaches the event horizon, time stands still and the star can collapse no more. It is a frozen, collapsing object, packing all of that bulk, many times the mass of our own sun, into such a tiny point gives black holes their powerful gravitational pull. Thousands of these stellar mass black holes may lurk within our own Milky Way galaxy. If we talk about different type of black holes, the black holes can be classified on several bases. Main bases in which black holes are characterized are mass, electrical charges, and angular momentum. First, on the basis of charges, it comprises of Schwarzschild, Kerr-Newman, Kerr, Reissner-Nordstrom. On the basis of mass, it comprises of Many black holes, stellar mass black holes, intermediate black holes, and supermassive black holes. On the basis of angular momentum, it comprises of rotating black holes and non-rotating black holes. Death of black holes. Back in 1970s, astrophysicist Stephen Hawking discovered something remarkable. Through a strange and not yet completely understood interaction between the event horizon and the quantum fields that make up reality, black holes can slowly evaporate. So they are not entirely black. They do give off a little bit of energy which causes them to lose mass. It's not much since a typical black hole will emit only one particle every year. But it's not nothing. Over time, they shrink down to nothing and simply pop away in a flash of energy. See, a few times more massive than the Sun will take about 10 raised to the power 100 years to eventually evaporate through a process known as Hawking radiation. Considering that the universe is only 13.8 billion years old right now, this will happen in far future. Let's come to our main topic, extraction of energy through black holes. After all this, you might be having a question. Is there a way to harness this renewable energy? As a massive star collapses in on itself, its core is compressed until it becomes a black hole. Since angular momentum cannot go away, the spinning star picks up speed as it shrinks and eventually collapses into a tiny yet incredibly fast spinning black hole. Once this occurs, the space directly around the new black hole is grabbed by the power of the new entity. This region is known as agrosphere. Light and other matter gets sucked into a black hole and cannot come back out. However, light and matter in the agrosphere could conceivably re-emerge through it, would be greatly changed by the intense force. This agrosphere contains converted kinetic energy from the black hole, so much in fact that you would need to move faster than the speed of light to stand still in this region. The agrosphere contains more than enough kinetic energy for the needs of humanity. But how can we tap into it? Here comes the role of Penrose process. The Penrose process. This concept, designed by Roger Penrose in 1969, realizes the fact that a process of energy transfer could occur in the agrosphere. He understood that you may need to move at light speed to stand still in agrosphere, but you don't need to be moving that fast to enter it. Imagine if you will slip into a whirlpool and instead of just floating along the ride, you start pedaling in the direction water is flowing. Your speed would dramatically increase to a point far faster than you can swim normally. Now, in this situation, you would simply fall into the center of the whirlpool eventually, as you would in a black hole. However, if you could leave something behind, you may be able to escape. In theory, a rocket fired into the agrosphere could separate into two halves. By firing rockets, one half would fall into the black hole, but the other could launch out of agrosphere but faster than it entered. To amplify this energy further, we would have to build a giant mirror around the black hole to amplify the energy, also known as making a black hole bomb. Fortunately, the object would have only to be 10 cm thick to work and a few large asteroids. Once the structure is in place around the black hole, we would need to open a section and shoot electromagnetic waves inside. After closing the opening, those waves will bounce around faster and faster. Some may get lost in the event horizon, but most will stay in agrosphere. This leads to the process known as super-radiant scattering. This is basically when similar waves interact coherently and become exponentially stronger. By opening another panel of massive mirror system, exponentially stronger electromagnetic wave could be absorbed and converted into massive amount of energy. Advantages and disadvantages of utilization of energy from black holes. So let's see the advantages. It is an incredible source of energy. It can be possible through proper technology and help in various ways. This may be our only option in the future. Disadvantage is lack of energy and we don't know how to harness this energy yet. Have you heard of white holes? Let me explain you. White holes are other side of the coin to black holes, or the time reversal as physicists describe them. White holes were conventions of general relativity due to the same equation for collapsed stars, resulting in black holes. Black holes pull things with no chance of escape, while white holes repels object. But any object already inside is free to leave. White holes are a solution to general relativity, but no one knows how one might form in reality. Black holes form when stars collapse, but reversing the process to get white holes doesn't make much sense, since an event horizon would explode into a functional star. It would be like an egg unscrambled itself. There are many reasons why white holes cannot exist. First of all, it violates second law of thermodynamics. Second of all, even if large white holes did form, they would probably won't hang around too long. Any outgoing matter would collide with the matter in the orbit and the system would collapse into a black hole. Nothing can enter white holes. Since nothing can enter the white hole, the remaining universe would have no impact on its source. Since nothing passes through the event horizon of white hole, we cannot obtain energy from the Penrose process from white hole as we did earlier from black holes. So there is another theory. So the possibility of white holes existing comes from Stephen Hawking's radiation in the 1970s that black hole leaks energy. If a black hole leaks energy, it will eventually shrivel up and die. So what happens if the internal record of all the things the black hole swallowed? It creates a conflicting between general relativity and quantum mechanics. Scientists Rabelli theorizes that the death of a black hole is the birth of a white hole. As the white hole leaks energy and grows small enough to no longer obey general rules, quantum randomness takes over, and the black hole transforms into a white hole. So, in conclusion, at the end, most of this is still science fiction and non existent. Maybe in the distant future, but the concept exists in reality today. What are your thoughts about on the future of energy? Do you think it resides in this space or do you think it's something undiscovered closer to home? Thank you for patiently listening to our project and hope you learned something from this project.